In this video, I'll be going over an introduction to exponential functions. So the kind of most basic form of an exponential function would be a times b raised to the x power. So when we have the input value in the exponent, this is what determines that a function is classified as an exponential function. Let's look at all the properties that we need to be aware of for an exponential function. So this list shows the properties for an exponential function. So we want a to be a non-zero real number. So something like this, f of x is equal to 3 times 2 to the x. So the a value is right here. This a value cannot be 0. It can be positive or negative. The b value must be positive, and it cannot be between, or it cannot be equal to 1. So for example, f of x, let's say the a value is still 3. We could have 3 times 0.2 raised to the x, or maybe f of x is equal to 3 times 2 raised to the x, or 5 raised to the x. Okay, so the b value must be positive, and it cannot equal 1. And then these next set of properties or characteristics can be visualized if we think about what an exponential function looks like from its graph. So here are two graphs. We would say the graph on the left is increasing. The graph on the right is decreasing. We get an increasing graph when b is greater than 1. We get a decreasing graph when b is between 0 and 1. Okay, so looking at both of these graphs, we can see that the domain is all real numbers. It passes through all the possible x values. The range, so when a is positive here, the range is from 0 and upward. And both of these graphs would fall into that situation. However, if a is negative, let's suppose I had this function, negative 2, 5 to the x, that negative is going to be a vertical reflection. So the graph would then be doing something like that. So in that case, the range would be from negative infinity to 0. And then the last point here, the y-intercept is 0, a. So a is always, we think of a as our starting point. We can kind of think of a like the, we can think of a like the y-intercept unless there's any sort of transformations happening. But this a value, we say that that's our starting point or the initial value. Okay, so the initial value corresponds to the y-intercept. And so that's what this is saying right here. And then the horizontal asymptote for both of these graphs is y is equal to 0. So it's this line here. So both curves are getting very close to that line, but never touching it. And same thing on this one when we have the graph flipped. So these are all characteristics for the most basic function. F of x is equal to a times b raised to the x. So if we have no transformations, all of these things apply. This example asks us to find an exponential function in the form f of x equals a times b to the x that passes through negative 2, 6 and 2, 1. So looking at the graph, if I graph these 2 points, that'll tell us whether this is going to be an increasing or a decreasing graph. So I have this point here, that's negative 2, 6, and then we have 2, 1. So the exponential function is going to do something like this. Okay, so this is going to be decreasing. So that tells us that the b value is between 0 and 1. Okay, so what we do is we take the form f of x equals a times b to the x. What we do is let's plug in both sets of ordered pairs separately. So first, when I plug in negative 2, 6, going to get 6 is equal to a times b to the negative 2. When I plug in the other coordinates, I get 1 is equal to a times b squared. So we want to do in these two equations, we want to ultimately solve for a and b. The a and b values will be the same in each of these. So what I want to do first is isolate either a or b in one of these equations. So we could do this in a variety of ways. I'm going to work with this first equation. 6 is equal to a times b to the negative 2. When b is raised to the negative 2, that means it's going to be in the denominator. So I'm going to multiply that equation both sides by b squared. So I get 6b squared is equal to a. So what I'm going to do is I'm going to take this, 6b squared equal to a. I'm going to plug it in right here. So I'm going to end up with 1 is equal to, in place of a, I'm going to write 6b squared, and then that's also getting multiplied by b squared. So we get 1 is equal to 6b to the 4th power. Divide both sides by 6, and then we're going to need a calculator because we want to take the 4th root here, or raise both sides to the 1 over 4. So 1 over 4. This is the same thing as saying 1/6 raised to the 0.25. That's going to be equal to b. So we get a b value when we punch that into the calculator. We get about 0.6389. Okay, so that's the b value. And then to solve for a, I can plug in that b value in any of these versions of the equations we came up with to solve for a. I'm actually going to use this version right here. So we end up with 1 is equal to a times about 0.6389 squared. Working this out, I get 1 is equal to a from the calculator. This 0.6389 squared is 0.408. Let's round to 2. Divide both sides. I end up with a is equal to 2.4498 about. So we have an a value, we have a b value, so ultimately we can put this all together into our function. F of x is equal to 2.4498 times 0.6389 to the x power. Okay. And we can check this answer. If we don't have a calculator, a couple things that we can check. Well, the a value here is going to be whatever the whatever the y-intercept is. So about 2.5. It's about right here. So in my rough sketch, that would make sense. That's a reasonable y-intercept there. And then the b value must be between 0 and 1 because it's decreasing, and we got a b value that's between 0 and 1. And if we have a graphing calculator, we can graph this this function that we came up with and verify that it goes through the given points. All right, here's another example. It says a wolf population is growing exponentially. So because this is growing, that means the b value, our base, is going to be greater than 1. In 2011, there were 129 wolves. By 2013, there were 236. Write the equation representing the population n of wolves over time, t. So we're looking for n of t. So t, or time, is going to be measured, or is going to be the input of the function. Using this model, how many wolves will be predicted to be in the population in 2015? What is the percentage change each year? Okay, so our function, let's just use the form we've been talking about. So we said that a is the initial amount. Well, the first year that we are given is 2011, so let's let that be year 0. So at year 0, so at n of 0, we get 129 wolves. So that means this is going to be the a value in the function. So n of t is equal to 129b to the t. And the reason that a is our initial value, well, if we think about what I just wrote here, this is saying when we input 0, we get 129. Well, if I input 0 into the exponent, the b raised to the 0 power is equal to 1, and so 1 times 129 gives us 129. So the initial value is just when we have an input value of 0. Okay, and then it says in 2013 there were 236 wolves. So what that means is n of 2 is going to be equal to 236. So how we do this is for the output value, we're going to do 236 is equal to 129. We know that that's our initial value. And then the input value was 2. So we need to solve this for b here. So divide both sides by divide both sides by 129, and we end up with about 1.8295, let's say, and then square root both sides. So we get a b value. When we square root both sides, we can get a positive or negative, but b always has to be positive. So when we square root, we get about 1.3526 as the b value. So writing everything together, our function n of t is going to be equal to 129 times 1.3526 to the t. Alright, so write the equation representing the population. So we did that. Using this model, how many wolves would be predicted to be in the population in 2015? So in 2015, that's when n is equal to 4. So what we're going to do is we're going to plug in 4 into the function. 0.3526 raised to the 4th. And we end up with about 432 when I round. 431.78 for, let's call it 50 wolves. Okay, so about 432 wolves after 4 years. So this is really growing. And then the next question says, what's the percentage change? Well, what we do to find the percentage change is we look at the b value. Okay, so this, how we could write this is 1 plus 0.3526. And this number right here corresponds to the percentage change. So to write 0.3526 as a percent, we would write 35.26%. We move the decimal 2 spaces. So that gives us the percentage change. So suppose I had a function that looked like this. N of t is equal to 129 times 3 to the t. Well, we take the b value. We can write that as 1 plus what is going to give me 3? Well, it's 2. So this corresponds to the percentage change. Move the decimal 2 spaces to the right, so that would be a 200% percentage change. So this last thing we're going to look at here, we have 3 tables, and we want to know, do the tables represent linear, a linear function, an exponential function, or neither of these? Okay, so for a function to be linear, we say it has a constant rate of change, and not just constant. What that means for it to be linear is we are adding the same amount each step of the way. So by saying constant, we say a constant additive change. So we are either always adding the same amount or subtracting the same amount. For a function to be exponential, we also have constant change, but we're multiplying each step of the way. So we have constant, we say multiplicative change. Okay, so we multiply by the same amount each step of the way. And then if we don't have either of these types of change, we could say the function is neither exponential or linear. So looking at each of these tables, let's start with, it's usually the easiest to see if we have a function that has linear change. So do any of the functions have the same amount that we're adding to each of the outputs? And if we look at the g function, what we're doing is each step of the way we're adding 3. Okay, Okay, so we'd say that this function is linear. Now, looking at the first function, f of x, looks like to go from 3 to 12, we're multiplying by 4. But then to get from 12 to 27, we're not multiplying by 4 anymore. Looks like we're multiplying by about 2 1/4 or something. So because the multiplying is not the same, this is not exponential. Okay, and then if we think about what we're adding each step of the way, well, here we're adding 9, but then we're adding 15, and then we're adding 21. So we're not adding the same amount each step of the way. So we're going to say that this is neither linear or exponential. Now for h of x, first step, looks like I'm adding, 9.25. Okay, but then in the second to the third step, I don't know off the top of my head, but it looks I'm adding more than 10. I'm adding over 14. So it's not linear. And then let's figure out what we're multiplying by to get from x equals 1 to x equals 2. Well, to figure that out, we can divide this number, 29.25, divided by 19.5. And what we get is 1.5. So here we're multiplying by 1.5. And then if we multiply again by 1.5, we get 43.88. Multiply by 1.5 again and again. So each step of the way we're multiplying by 1.5. So we would say that this function is linear.